For nearly a century, nuclear fusion has been the holy grail of clean energy, the ultimate promise of infinite, carbon-free power. But in 2026, it is finally transitioning from a distant laboratory dream into an industrial reality. The core challenge has always been confinement, keeping hydrogen isotopes squeezed under extreme pressure and temperature. For decades, this required massive, heavy, and costly electromagnets based on Soviet-era designs. The breakthrough that changed everything is the advent of high-temperature superconductors, or HTS. These advanced materials, manufactured as flexible REBCO tapes, operate at liquid nitrogen temperatures rather than near absolute zero. By generating magnetic fields up to 20 Tesla, HTS magnets can contain plasma 10 times more efficiently. This allows engineers to shrink the physical volume of a Tokamak reactor by a factor of 10, radically lowering construction costs. Inside these compact devices, isotopes of hydrogen, deuterium, and tritium are heated to temperatures exceeding 100 million degrees Celsius. At this million-degree threshold, atoms collide, fuse, and release massive bursts of energy. This miniaturization has triggered a structural shift. Instead of relying solely on massive international scientific consortia, agile private startups are now leading the charge, building reactors in a fraction of the time. Squeezing this volatile hydrogen plasma requires state-of-the-art vacuum chambers. By utilizing complex 3D-printed metal alloys, engineers can design complex cooling channels directly within the chamber walls to handle extreme heat fluxes. This technological pivot has unlocked a massive flood of private sector capital. Over $6 billion of venture funding is currently accelerating the commissioning of private fusion reactors around the globe in 2026. At the forefront of this commercial space race is Commonwealth Fusion Systems. Their SPARC reactor, slated for commissioning in 2026, is designed to be the first magnetic confinement device to achieve net energy gain. Net energy gain, or Q greater than 1, is the holy grail of fusion physics. Crossing this scientific break-even threshold means the fusion reaction generates more heat energy than the massive magnets consumed to run it. Other startups are pursuing radically different configurations. Helion Energy is developing a magneto-inertial fusion device called Polaris, which compresses plasma to directly extract electrical energy without steam turbines. Helion's confidence is backed by a historic contract, a power purchase agreement signed with Microsoft to supply commercial fusion energy by 2028, specifically to power the massive energy demands of artificial intelligence data centers. Meanwhile, laser-driven inertial confinement fusion is also breaking records. Building on the National Ignition Facility's historical breakthrough, researchers are using intense ultraviolet lasers to compress tiny fuel pellets. By merging magnetic confinement with inertial compression, magneto-inertial fusion offers a compelling middle path. It combines the stable containment of magnets with the extreme density of laser-driven systems. Yet, massive engineering hurdles remain. Breeding tritium fuel in real time requires lining the reactor walls with lithium-breeding blankets, which absorb neutrons to generate the necessary tritium isotopes. To handle the massive thermal exhaust, reactors utilize complex magnetic diverters. These systems act as the reactor's exhaust pipe, routing excess heat away before it can erode the structural steel walls. Controlling the turbulent, unstable plasma requires split-second adjustments. Startups are deploying advanced machine learning models to analyze plasma behavior and adjust magnet currents in under a millisecond. If successfully scaled, these compact reactors could democratize energy globally. A single 100-megawatt fusion plant could provide continuous, clean power to entire cities, factories, or container ships. This has sparked a new geopolitical race. Nations are competing fiercely to secure the manufacturing supply chains for high-temperature superconducting tapes and the raw rare earth materials needed to build them. As we cross into 2026, the era of theoretical fusion is ending. By miniaturizing the sun inside 3D printed steel chambers, we are paving the way for a carbon-free future powered by the ultimate source of energy.